Hi everybody, we're in week 3 now, term 3. Where's the time going, right? So we are getting into the chemical synthesis, and the part of this is also chemical analysis. So you'll learn about chromatography, infrared spectroscopy, and gel electrophoresis. We're going to start simply with chromatography. All right, so chromatography is a method we can use to separate organic compounds based on their chemical properties. Polarity, size, their charge, being 3 of them. So chromatography, you guys should have all done it before. Thin layer chromatography, some of you will have done this as with paper and ink. Column chromatography, where we slowly drip our sample through the column. HPLC, which is where we force it through under pressure. And gas chromatography. We'll only really cover TLC, column, and HPLC in uniform. I hope you guys got your writing pens on. There's a fair bit with this one. So chromatography has a solid or stationary phase and a mobile phase. Mobile phase being the solvent which has the solute dissolved into it. Some terminology. So to adsorb is to adhere to the stationary phase, or the column or the paper. To desorb, it's dissolving into the solvent. And the level of adsorption and desorption depends on the polarity of the molecule in question. So carefully remember adsorption, the adhesion of the molecules to the surface of a solid. So there's varying simplicity levels, that's a good word, of chromatography. We have paper chromatography, all the way up to being able to separate millions of proteins in a sample to individually identify every single one. So paper chromatography is the beginning. Paper, especially chromatography paper, has capillaries running through it. The water will travel up the capillaries from the start, and it will finish at some point dependent on how much of the solvent is there. The solvent is the mobile phase. If we were to put the sample at the base, that is the origin. As the solvent moves up, it will dissolve the molecules, and the molecules will travel up the paper depending on their properties. So the length of travel depends on the molecules themselves and the solvent. Who remembers their golden rule for solvents? For, what's the word? Dissolvent. How much they dissolve. Like dissolves like. Yeah, like dissolves like. So the paper itself is the stationary phase. The molecules adsorb to the paper, and when the mobile phase or the solvent goes past, they will dissolve into the water dependent on their chemical properties. So I want everyone to draw that and label it. So the solvent is the mobile phase, paper is the stationary phase, and the solvent will move up, and it will carry the molecules at the starting line up the paper, and the distance it travels, or the sample travels, depends on its polarity. So here we're on 30 seconds to draw that. So the rate of the movement of each substance, or the components within the substance, depends on how strongly it adsorbs to the stationary phase, or how readily or not it dissolves. So we have black ink on the bottom. As the water or the mobile phase moves up, it's dissolving, because there's no such thing as black ink. It's just it's made of other colors. So it's going to separate the colors. If it's water, it's going to separate them based on how polar or non-polar each of those component inks are. So everybody write this down 1,000 times. Like dissolves like. So if we use a polar solvent like water, the more polar molecules will dissolve more readily into the water. So they will spend more time in the water, and they will travel further along the paper than the less polar molecules, because they are not as strongly dissolved into the solvent. So if you're using water, the further it travels, the further the molecules travel, the more polar they are. So we can separate organic molecules based on their different properties. So we can stick our leaf stain onto the bottom of the paper, put it into water, and the most polar molecules will travel the furthest. Which of these molecules here is the most polar? Oh, we have a, so carotene travels the furthest, it's the most polar. If we were using alcohol, a non-polar solvent, would we see a different picture? Would we see the opposite? So chlorophyll B would travel the furthest if we used something like, what's a polar? Phenol, which is a non-polar solvent. Okay. There is, and everybody laughs, the retardation factor, or how far the distance, how far the component travels from the origin divided by the total distance that the solvent has traveled. When you use the same conditions, you can compare that to known reference values and somewhat figure out what the molecule in question is. So, what is the RF value for these three spots? Or those two spots, sorry. So for the first blue spot, what would the RF value be? If it's the distance that the component has moved divided by the solvent front movements. 0.3 and 0.7. Very good. So here we have a question. We have two samples. One is the lolly, the other is fructose, and the other is glucose. How do I know that the lolly sample contains glucose? So the known glucose sample on the right is the same as the first spot in the lolly sample. Paper chromatography is a crude method in comparison to others. So, which of these components is the most polar if we're using water? So most polar is B. Which one's the least polar? Perfect. So C has traveled the least distance away from the origin, so it is the least polar. So column chromatography is roughly the same thing, but we are separating them through what you'd call a porous gel. So instead of the paper, we're now using a porous gel column. So we put our sample on the top. It's under no pressure, it's just dripping through under its own steam. Component 1 is here, component 2 is here, component 3 is here. Which one of those is the most strongly dissolved in the mobile phase? Or the most dissolved? Component 1, 2, or 3? So, what's going to happen is that the components are going to come through and separate based on how absorbed they are or dissolved they are. This isn't great because all it does is separate. Then usually you have to wash the column out to get the components to come out. So this is where I'm getting a bit more hardcore. So high performance liquid chromatography. You also have fast protein liquid chromatography. Ironically, this takes about 48 hours, this process. So it's not exactly fast. I don't know who came up with that name. So we still have the mobile phase. We still have the solid phase, which is just a porous gel. But we're doing it under pressure. So now we don't want them to be trapped on the column. We want them to separate and come through the column based on their physical properties. So we have the big difference here is we have a detector and a recorder. Now, sometimes it's not waste because you want to catch what's coming through as well to test it. But for this, all we're really caring about is what's coming through and what's not. So as the liquid's going through, the detector is actually shining UV light through this box, and it's detecting when something that isn't water is coming through. It then records that. So now we can actually figure out what's coming through and when. So here we inject our black ink through the column. After 1 minute, we don't see any peaks. After 2 minutes, still nothing. The red has come through first because if this was water, it's the most polar. It's going to come through that column, and it shouldn't really be called a solid phase because it's not solid. Otherwise, nothing would pass through it. It's like a semi-porous gel that's got like literally beads inside of it. And then after 3 minutes, the red component comes out. At 5 minutes, the blue component comes out. So if we're using water, what is the most polar molecule here, the red or the blue? So yeah, exactly. It's like paper chromatography, just slightly different. The red is going to come through faster if it's a polar. So these peaks tell us that after a certain amount of time, the red component is coming out. It also tells us in relative terms how much of something there is. The bigger the peak, the higher the concentration compared to all of the other components. So here at 2 minutes, we registered a peak, 6 minutes registered a peak, and then 9 minutes again. So what is, so if this was in water, which one of these would be the most polar molecule? Which peak, 1, 2, or 3? The peak at 2 minutes, yeah. I don't understand how teachers make this so complicated. It's a very, very simple concept. Shorter time, it spent more time dissolved. Longer time, it spent more time stuck on the column. So here, if your chromatogram looks like this, you've done it terribly. But, so, let's say testing someone for diabetes, so we want to see if their pee has insulin in it, or their blood has insulin in it. We run our chromatograph with pure insulin to see what it looks like. Oh, hang on, my speaker. So here we have a spike at about 7 minutes of pure insulin. That's what it's supposed to look like if there's insulin in our sample. Oh, hey. This is our bodily fluid. We've run it through the chromatography column. And this is our chromatograph. Shush, speaker. So each time a component passes through the detector, you get a spike or a peak, for lack of a better term, spike or a peak. The height of the peak tells us the relative concentration. So I'm going, the computer's telling me that's insulin. It looks like insulin. And if the height of the peak tells us the concentration, what should we see if I add pure insulin to the sample? What should happen to that spike or peak that I think is insulin? If I spike that with pure insulin, and what should happen is this peak here should get bigger. So this is the sample on the left of pure insulin. We've got a peak at about 6 minutes, 6.5 minutes. On the right-hand side, we've got insulin. What we assume is insulin because we're comparing it to the pure sample. Now, to confirm this, what I'm going to do is add some pure insulin into this. By doing that, what we should see is the height of the peak increases. So we take the sample, we add pure insulin, and what we should see here is an increase in the peak size. So if we deliberately add additional insulin, we will get an increase in the peak height. So that's how we can run a confirmatory test. Yeah, my voice started to go again. God's sake. Okay, forensic chromatography. So we can compare an unknown substance against a known sample. So anybody like eating like fancy Manuka honey? Like proper honey. What they will do is they will take honey, expensive honey, and add cheap honey and sugar syrup to make it go further. If you were to run a sample of pure Manuka honey and the spiked honey, what do you think would you see a completely different chromatogram? Would they look completely different? Hopefully. So on the left, we have our pure olive oil sample. And on the right, we have our suspect shipment. So can you see the difference there? They look like completely different products. You can do this with perfumes, you can do this with alcohol, you can do this with pretty much anything you can stick in a chromatogram that people like to fake. Anyone ever watch Bones or NCIS or anything like that? They go, let me put it in the mass spec. And they go, this leaf sample came from this part of West Virginia. And you can actually tell where certain things have been made when they are looking at illicit drugs and shipments of illicit drugs. What they do is they have a bank of, this is what drugs from Mexico look like. This is what drugs from Belarus look like. What drugs from, made in Australia look like. So when they seize a shipment of drugs, they'll put it through a mass spec, and then they can compare that to the known illicit drugs from other countries, so they can determine the country of origin. There's only a few labs in Australia that are allowed to test illicit drugs. Anyone want to hazard a guess why? No one? So in order to test illicit drugs, you have to have a pure sample. So, Kai, yes, exactly. People like drugs. Most street drugs are like a few percent actual drug and the rest are like fillers, right? So in the fridges in these laboratories, you have to have reference samples of methamphetamine, cocaine, to test against the drugs that are found on the street. There's been plenty of cases where, unfortunately, someone has gone in and taken the pure reference sample and replaced it with something else, or watered it down to make it look like there was none missing. So meaning every sample that had been tested had to be retested. So, oh man, sorry. Okay, do some practice questions. I'm not going to be able to do any more after these. My voice, I do apologize. So how many different components are present in sample B? So there's 2 colors present in sample B. So which color of sample A is least strongly absorbed on the stationary phase? Blue, yep. Or it is the most strongly dissolved. Which of the 2 samples are likely to have one component in common? A and B, correct. They both have the blue component. So don't worry about that one. Okay, so looking at HPLC, which part of the chromatogram, so you've got the time, then you've got the height of the peak, which is used to identify the components. Is it the time or the height of the peak? Kai says the time. Kai would be correct. So which would be least affected by a change in concentration of the sample components? Time again, yeah. So which is used to determine the concentration of each component? Peak height, very good. Okay. So we've added some difficulty here. We have our 4 primary alcohols, A, B, C, and D. We have a non-polar stationary phase and water and methanol as the mobile phase. What order would you put the alcohols in from most polar to least polar? Yeah, because the stationary phase is non-polar. So the polar alcohols are not going to stick to it. They'll be repelling each other. So what about the concentration? Highest, or lowest to highest? D, C, A, B. Perfect. So I'm going to send you these slides in this recording, and I want you guys to have a go at this extension question. We're not going to do it now because it's quite lengthy. So I'm going to send you these tonight or tomorrow once I get the recording done. Sorry. And I'm going to stop the recording now because I can't speak anymore. I'll do some extra recordings at some point, another makeup, but I just can't speak for longer than about half an hour like that. So I will see you guys next week. I'll probably, if my voice is all right, do maybe an hour and a half, do 2 separate recordings. It's just my voice, guy. I had a cough like 3 weeks ago, and because all I do is talk, I just never recovered. My voice never recovered. So, all good. I'll get over it eventually. I will see you guys in a week or so.